This paper, titled Galactic Gravitational Field Measurements, an extension of emergent gravity through modulation-based field theory, authored by Christopher Young, addresses the long-standing problem of explaining galactic rotation curves without invoking dark matter. The purpose of the paper is to propose an alternative theoretical framework that extends Verlinde's emergent gravity theory by introducing a modulation-based field approach centered on energy flow dynamics originating from supermassive black holes and propagating through an auxiliary modulation coordinate. The paper aims to provide a comprehensive mathematical model that accounts for observed galactic rotation profiles and offers testable predictions. The background to this work lies in the persistent astrophysical puzzle first identified by Vera Rubin and Ford in the 1970s, where stars and galaxies, such as Andromeda, maintain nearly constant orbital velocities, regardless of their distance from the galactic center. This contradicts classical Newtonian expectations, which predict a decrease in velocity with increasing radius due to decreasing enclosed mass. Subsequent extensive observations across various spiral galaxies confirmed these flat rotation curves, challenging the conventional understanding of gravity and mass distribution. The dominant explanation has been the dark matter hypothesis, positing invisible, non-baryonic matter halos surrounding galaxies to reconcile the discrepancy between observed gravitational effects and visible mass. However, despite decades of research and increasingly sensitive experiments, direct detection of dark matter particles remains elusive. Additionally, dark matter models face challenges such as the need for fine-tuning halo distributions on a per-galaxy basis, small-scale structure inconsistencies, and philosophical concerns about introducing undetectable entities. These limitations motivate the search for alternative explanations. Emergent gravity, as proposed by Verlinde, reconceptualizes gravity as an entropic force arising from thermodynamic behavior of microscopic degrees of freedom rather than a fundamental interaction mediated by particles. Building on this, the paper introduces the auxiliary modulation coordinate, a structured energy field existing alongside spacetime, which encodes energy dynamics, quantum behavior, and field interactions as resonance patterns. This coordinate is not a speculative hidden dimension, but a computable field derived from modulation principles. The key components of this field include quantum waveforms, field curvature modulations, energy current propagation, and temporal modulation. The core mathematical framework employs entropy-resolved resonance profiles, a non-iterative method collapsing complex field interactions into single-step harmonic solutions through entropy modulation and universal harmonic weights. This approach aligns conceptually with Verlinde's entropy-based gravity, but offers explicit computational tools for modeling energy flow and spacetime structure. The paper's theoretical foundation rests on three pillars. First, supermassive black holes act as energy nodes, converting accreted matter into energy that enters the auxiliary modulation coordinate. Second, this coordinate serves as a dynamic carrier of modulated energy, propagating structured flows. And third, a generalized modulation-based field equation governs the spatial, temporal, and modulation dynamics of energy propagation. This framework treats galaxies as dynamic energy flow systems sustained by continuous energy injection from central black holes rather than passive mass aggregates governed solely by gravitational attraction. To ground the model quantitatively, the paper analyzes Sagittarius A Stir, the Milky Way's central supermassive black hole, using observed mass and accretion rates to estimate an energy output on the order of 3.58 1042 joules per year. This energy drives the modulation coordinate field, initiating energy flow patterns that sustain galactic structure. The gravitational pressure at the Schwarzschild radius of Sagittarius A Sty is calculated to be approximately 3.7 times 10�6 newtons per square meter, providing the initial condition for energy injection into the auxiliary modulation coordinate. Energy propagation through the auxiliary modulation coordinate involves four dynamic processes: information flow maintaining coherence, baseline resonance serving as a carrier wave, rotational processes imparting angular momentum, and localized structures creating stable energy packets. These processes combine into emergent resonance modes that modulate spacetime curvature and rotational motion via harmonic pressure gradients. A key result is the non-uniform distribution of energy flow within galaxies. Approximately 90% of the energy propagates through spiral arms, acting as primary conduits sustaining structure and star formation, while 10% flows through interarm regions, stabilizing the overall galactic energy balance. Energy density in spiral arms decays exponentially with radius, with characteristic scales consistent with observed galactic dimensions. The interarm regions have lower energy density distributed over larger volumes, explaining their reduced matter concentration and star formation rates. The paper models energy propagation using a modified wave equation coupling spatial and modulation velocities, yielding standing wave patterns along spiral arms corresponding to observed star-forming regions. This model extends beyond dark matter halo profiles by deriving galactic structure from energy flow dynamics with fewer free parameters, providing a more parsimonious and unified explanation across galaxy types. The framework is applied to various morphologies. Spiral galaxies exhibit concentrated energy flow in arms with exponential decay. Elliptical galaxies show more uniform energy distributions, with gradual radial decay and no arm structure. Irregular galaxies have chaotic but coherent energy patterns with star formation as secondary energy sources, and lenticular galaxies show concentrated central energy with disk-like distributions. This universality contrasts with dark matter models, which require galaxy-specific halo parameters. Space-time curvature arises directly from local energy density modulated by a space-time elasticity factor, which varies radially. The relationship is expressed as curvature proportional to energy density times elasticity, scaled by fundamental constants. Spiral arms, with higher energy density, create pronounced curvature responsible for gravitational attraction and matter concentration, whereas interarm regions exhibit lower curvature consistent with their observed properties. At galactic edges, energy densities from arms and interarm regions combine and elasticity reaches a maximum, forming a low-resistance zone, or LRZ. This zone features minimal resistance to rotational motion and naturally explains the flat rotation curves without invoking dark matter. Calculations show that the LRZ corresponds to a boundary condition where curvature and elasticity balance to sustain constant orbital velocities. This phenomenon extends Verlinde's entropic gravity by providing a concrete mechanism, energy flow through the auxiliary modulation coordinate, coupled with variable spacetime elasticity, that manifests as emergent gravitational effects at galactic scales. The LRZ forms consistently across galaxy types, with morphology-dependent characteristics, well-defined in spiral and lenticular galaxies, less pronounced but present in ellipticals, and variable in irregulars. This consistent formation supports the framework's universality and parsimony compared to dark matter models requiring distinct halo profiles. The paper further quantifies the resistance reduction in the LRZ via a resistance coefficient dependent on combined energy density and elasticity. At the galactic edge, this coefficient approaches a minimum, enabling sustained rotational velocities matching observed flat rotation curves. Finally, the framework proposes several observational predictions to empirically test the LRZ concept and the energy flow model. These include subtle polarization effects of light passing through the LRZ due to altered spacetime properties, distinctive emission signatures in radio and millimeter wavelengths at galactic boundaries, characteristic transitions in velocity gradients observable in detailed rotation curves, and interactions between the LRZ and intergalactic medium detectable via absorption line studies. These predictions go beyond current dark matter detection efforts and offer specific avenues for validating or falsifying the proposed model. In summary, this paper presents a mathematically rigorous and physically grounded extension of emergent gravity theory, replacing the dark matter paradigm with a modulation-based energy flow framework. By situating supermassive black holes as central energy sources and employing the auxiliary modulation coordinate to model structured energy propagation, it provides a unified explanation for galactic rotation curves, structure formation, and spacetime curvature. The introduction of the low-resistance zone at galactic edges offers a natural mechanism for flat rotation curves without additional mass. The framework's applicability across galaxy types, alignment with key empirical observations, and provision of testable predictions mark it as a significant advancement in alternative gravitational theories and our understanding of cosmic structure and evolution.